All right, hey folks. Last day of lectures that I'm assigning. We made it through the 16 weeks. Good job. Just a couple videos for the day, and we'll be done. All right, let's get into it. Okay, so let's talk about radiometric dating, specifically radiometric carbon dating. So this is pretty cool the way this works, and it's really intuitive that people figured out how to do this. Okay, so the radiometric, specifically carbon dating, occurs via the following. So it starts with nitrogen in our atmosphere is bombarded by cosmic rays, and specifically this is nitrogen in the upper atmosphere, way up there at the edge of space. Okay. And so through this process, we create unstable carbon-14, more than what would be present naturally. Okay. So as you can see here with our reaction, a neutron slams into a nitrogen-14 nucleon, and then you make this carbon-14, and a proton is also kicked out in the process. Okay, so if we add up all of these things, this all is conserved and checks out. Okay, this process now, this carbon-14 will undergo beta decay with a half-life of 5,730 years. And this carbon-14 that's been placed in the atmosphere, like I said, above the natural abundance, will get taken up by plant life, for example. Okay. So as long as a tree or another plant is alive, this uptake of specifically carbon dioxide containing a carbon-14 will remain in steady state. Okay. And so, of course, there will also be some amount of just ordinary carbon present, carbon-12. All the same, as like I said, as long as the plant or the tree or whatever is alive, the ratio of carbon-14 to carbon-12 remains constant. And that's roughly 13.6 decay events per minute per gram of carbon. This is not a number that we need to memorize. It's just a number that's been well characterized. Okay. However, as soon as the tree dies, it stops taking up carbon dioxide, right? And now this carbon-14 ratio will change. So the carbon-14, whatever is remaining in the tree, that carbon-14 will decay. Okay? And so this ratio of carbon-14 to carbon-12 can tell us how old it is. So specifically, I'm talking about trees because archaeologists have recognized artifacts that humans use are predominantly made of trees. Go figure, right? Scrolls or other tools that might have been used many thousands of years ago. And from that, we can age how old those tools or scrolls might have been. So here's an example problem. Okay. So the carbon-14 content of a wood harpoon handle found in the remains of an Inuit encampment in western Alaska is 61.9% of the carbon-14 content of a same type of wood from a recently cut tree. How old is the harpoon? Okay, so the challenge of this, right, is that if you want to date some type of artifact, you do have to find living material that artifact was made out of so that you can compare. Okay. So all the same, we can still calculate this, and we can do this using our first order integrated rate law. Okay. So the first thing we have to get is a rate constant, knowing the half-life of carbon-14. And so I just gave that to you. So we said the half-life was 5730 years. We know the half-life of a first-order reaction is 0.693 divided by K. So I'm going to rearrange that to get a rate constant out of that. And so that's 0.693 divided by T 1/2. And I'll plug in, right, that, let's see, 5730 years for the half-life, okay? And that'll give us a rate constant in 1 over years, and that's perfectly fine, right? This radiometric dating is a slow process, and it is meant to be over periods of years or even centuries, right? Okay, so we get something like, I'm going to put that in scientific notation, 1, 2, 3, 4. So 1.209 times 10 to the minus 4, 1 over years. Okay? So now we have a rate constant, and we want to use the integrated first order rate equation. So that's natural log of AT equals negative KT plus natural log of A initial. And we want to solve for time. So I'm going to rearrange this to be natural log of AT minus natural log of A0 equals negative KT. Hopefully we remember we can do a log trick here, or if I subtract the logs, I can now write them as a ratio, and that equals negative KT. And then finally, I can solve for T by dividing both sides by the negative rate constant, and that will give me time. How old is the sample? Okay. Well, so now you notice that we don't have an AT or an A0, but instead, because someone did a careful experiment and they found the same type of wood from a recently cut tree, and it was 61.9% of that carbon-14 content, then we can replace this ratio with 61.9% expressed as a decimal. Okay, so now over here we can say T equals the natural log of 0.619. So I just took that percentage, right, and divided it by 100. And then now that's going to be divided by negative 1.209 times 10 to the minus 4th, 1 over years. And so let's do that calculation. So I can say 0.619 and then natural log. And then now that's divided by 1.209 e to the 4th power negative, and I forgot to put a negative sign in there. So we recognize that we can't have negative years, so that negative sign will go away if I had put that negative sign into my calculation. And we get something like 3,967 years. Okay. So pretty cool that we can do that with careful measurements and calculation. Okay. So this was a discussion of radiometric carbon dating, right? But if we circle back to this U-238 decay series, and I mentioned this earlier, but we could do radiometric dating calculations based on uranium if we want, or even perhaps another radioactive nuclide, as long as we know what its half-life is. And so depending on how old the sample is that we want to date, that's the particular radionuclide that we would choose. So for most human stuff, carbon dating is perfectly fine because we're talking about things over thousands or tens of thousands of years, at least in, if we're looking at things like scrolls made out of paper or tools made out of wood, okay? But if we wanted to age stuff that's much, much older, we would need to look at, the uranium decay series or perhaps another decay series. Okay, folks, I'll see you in the next video.